Our next talk is by Drazen Orescanin, who is president of the board at Poslovna Inteligencija. Drazen has more than 25 years of experience in projects in largest companies in Europe and Middle East, and has advised many communication operators from Deutsche Telekom Group, Telenor Group, Telekom Austria Group, Liberty, and Saudi Telecom Company. His today's lecture is named Conceptual Framework for Entity Integration from Multiple Data Sources. So the floor is yours.
Thank you. So I'm really glad to be here with this talk. Maybe just a few words of introduction. Actually, this talk is a result of these three institutions that you can see listed down of the bottom of the screen. It's Faculty of Electrical Engineering of University in Zagreb, and I'm on my PhD. North Carolina State University Department of Computer Science, where I did my research for the PhD, and Poslovna Inteligencija as the company that supported me in my PhD. And right now I would like to have this clicker to change the slides, so it would be really helpful. Great, thank you so much. So, a few words about who am I. So this is my family. I'm very, very happily married, and my daughter is now 16, and we like to spend time together and travel. And do you recognize the city where this photo was taken? I don't have any goodies, but it's Porto. I also like to ride my bike. We have a dog, and actually we currently have a new puppy, so we have a lot of fun back home. And yeah, I think you know now all about me that you need to know. So I would like to start with one quote from famous Greek philosopher, that there is nothing permanent except change, and basically change and pace of everything what we are doing is actually opportunity to develop new things and work in new fields. So we are currently faced with digital transformation, with growing data volumes, and increased requirements related to data privacy, and this is leading us to today's topic. So what is entity resolution and integration? Do anybody here in the public has any either scientific or practical experience in that field, in data matching, entity resolution? Yes, you can raise your hand. Okay, one. Good. Anybody else? Two. Okay, great. So, basically this is the process where you integrate different data from disparate sources that can be in different formats, have different attributes, and basically data that you are matching is not the same, but it is similar. So you need to use different algorithms that use statistics to find the likelihood and score how different entities from different sources are similar, and if they are match or they are not match. And this whole process is part of one a bit bigger and broader process that also includes data acquisition, profiling, cleansing, schema alignment, and also data fusion that will result in consolidated entities. How does it look like? This is like a standard example. So first, when you have data from one source, you do the profiling, and then you do the parsing. So you can see what is here first name, last name, what is address, what is zip code or postal code, what is region or county or state. Then you can apply another set of algorithms to correct the data and also to standardize the data. So in this case, we have some misspelling of city and part of the city. We also have a wrong zip code. We have a name that is spelled with the lowercase, and we should correct it as capital case. And when we do this part of cleansing and standardization and data preparation, we are matching and joining this data with data about the same entity from another system. And after matching, we create a merged, like golden record that describes this entity in more details. And after that, we are using another set of algorithms and logic that will enhance this data with additional information we don't have in source system. So basically, this whole process is then called entity integration, and such a process is behind many of the stuff we currently know. So a lot of search engines and legacy migration applications are based exactly on this kind of algorithms to prepare data. Also, those algorithms are implemented in various data profiling, data quality platforms that are commercially available. And basically, when we group some of these steps, parsing, correcting, and standardizing is part of data cleansing process, and fusion is consisted of merging and enhancing processes. So what is then the problem? We have the algorithms, we have the data, we have the target, what we want to do with those data, but different applications, different sources, different formats, different databases. It is not easy to find the data that describe same entity. And it's even harder to resolve it, to find the golden record. Also, you have to respect different data privacy regulations. So currently, GDPR is most known in Europe, but there are many others emerging worldwide. And you have to make sure that this data will be regularly updated with new records and with changes from existing data sources and from new data sources. And everything in this field is based actually at this picture. This picture and this diagram is relatively simple, and it's published by a guy who is a real guru in that area, Peter Christen. He sounds like a Danish guy, but he's actually an Australian guy. And everything is actually based on the process where you prepare and match and resolve two data sets. And basically, when you are able to do this with two data sets, then you can generalize the whole process for many data sets and many other scenarios. So basically, you have two databases. You do the data pre-processing. This is part of data cleansing and data quality preparation and standardization. Then you do something that's called indexing or blocking, which is a very important step, because if you have two really big data sets, for like example, I don't know, 100 million records in each of the data sets, and when you compare each of those records to any of the records from other data set that can be potential match or pair, then you will not have powerful enough computer in this world to do this, because some records are very, very different, and there is no sense to compare them to find if they are potential match. So in this step of blocking and indexing, you are using algorithms to find what records can be potential match, and then you cluster them in smaller blocks with 1,000 or 2,000 or few thousand records, and within those blocks you are then doing one-to-one comparison. After comparison, you do the classification and scoring, and you actually have like 3 sets of data. One that are considered as a match, that usually records that are similar 95 to 100%. The second group is clerical, so those are potential matches which require human intervention to decide what is the match. And you have non-matches which you discard from the process entirely. And after evaluation of those 3 data sets, you actually get the resolved entities that you can use in further process. So there are like some 4 standard requirements for this process. So effectiveness, so to get a high quality result. Efficiency, so it can run fast for big data sets. Genericity, so it can run online, offline, in streams. And low manual effort self-tuning, and this is something that is quite hard to achieve. And what researchers are doing in this field is actually they're trying to make something that is called F1 score higher. So this is actual ways, I will not go in more detail in this picture, but if you are in algorithms, you know this. So basically, they're trying to get algorithms to work with better precision and better recall to score better results. And you have many teams in different universities worldwide that are working on existing algorithms and open data sets where they are coding in Python and R and trying to improve those performances. But since every team is working on some small part, or algorithm for blocking, or algorithm for matching, or algorithm for enhancement, there is no big picture that academia is working on, because everybody is trying to make some kind of small improvement in the field and get some papers or books published. And this is reviewed by peers, and those advances are really nice. But is this something that business users and end users really need? So what are the real life challenges? So you have the situations where you need to match more than 2 data sets, so you need to develop the processes for that. You have situations where you don't have defined semantics, so you need to recognize the data, what is in the data set, and define the semantics, but this semantics can be done with non-exact relationships, so you can have like probability based semantics. Schema alignment, so you will have different data sets that describe same entity, but some of them have 10 attributes, some of them have 15 or 20 attributes, and like 120 attributes they can describe this same entity, and which attributes are important and which attribute will we use. Also matching of real-time and streaming data, because this is important for search engines, so you need to update the information as quickly as possible. For example, like 10 days ago, if you put in search engine Hurricane Florence, you will not get anything. But every hour, all these search engines should be updated with information about that hurricane, because this is how the news and information is created all over the World Wide Web. Incremental matching. So when you create, when you have like 10 different sources of data and you create golden records and then you match the records from all that sources, what happens with the new data? What happens when you have like 500,000 records in one source and 10,000 records in another source, and when you have like 11th data source? How you will handle this stuff automatically and with low maintenance? Changes of matching rules. So sometimes there is a need to change the rules and maybe to strengthen the rules that you used to match some data, and that will result in breaking some existing resolved matches and creating new matches. And this is also something that happens in real life. And of course, the problem of performance with large data sets. And basically, all of that stuff, or most of that stuff, is defined as human in the loop. So human in the loop is actually a process where you cannot handle everything just with programs and code and platforms and solutions. And you need actually humans to train, tune, test, and develop the models. So what we as humans are doing, we are doing tokenization and labeling of data. We are choosing the algorithms that we will use. We are tuning those algorithms and we are reviewing results of what we have done, and we are testing what we have done. And there are some questions that we are facing. How important is to have F1 score 1% better or 5% better performance? Are those improvements will result in some really big business benefits? And the most important, do we know what we are doing? And are we doing the right thing? And how much time we will use spending in working or developing on something that will lead us in a wrong direction and not in a direction that will solve our problem. And also very important observation is that the problems that you have when you are designing and developing those kind of models are much different than the problems that you have in production. So in development, you have a lot of steps and iterations, but in production, you are also very much concerned about performance. And what is the conclusion is that what academia and research is doing and what actually business needs is not synchronized. So everybody goes part ways. And the fortunate thing is that it is recognized. So there is a project called Magellan, and this project is actually about development of open source entity matching system by Madison University of Wisconsin. This is an open source project. It's based on Python, so it has Python libraries. You have the packages. You have all the code and Jupyter notebooks available on this link. And its results are described in 2 published papers. So one is at VLDB, and this second one is very important. It was on Hilda workshop last year, about human in the loop challenges for entity matching. And basically what guys from University of Wisconsin concluded is that you have a lot of pain points and different steps in the process when you are developing the model, and there are actually two reasons for that. First reason is you think you know what you are doing, but when you do what you thought that you need to do, then you find out that you actually didn't know what you needed to do, so you need to do everything again. And the other thing that is happening is that you don't have a clue what you need to do. And basically this is tested with Walmart and several other huge American companies, and actually this is the feedback that they got from testing in the field. So they have made several recommendations, and the first one is that end users need guides how to do things. The second one is they need to develop some tools for pain points in the process. Tools in the loop and human in the loop activities should be combined in this process, and they are not independent from each other. And the last one is develop a how-to guide for concrete, complex, real-life scenarios. So this is then the part where I have joined the party. And basically those scenarios are resulting in some new frameworks for those activities. So frameworks for entity matching and resolution already existed, but they were focused basically on matching two data sets. So if you remember this diagram from Peter Christen, all those frameworks were doing that. And there were several of them, so I mentioned just a few, Taylor, Faber, and STEM. But what we need a more general framework that will follow some specific scenarios. So in those frameworks, other steps in the process, so these general steps that are out of matching two data sets. So those existing frameworks, they have, I don't know, 5 or 6 different algorithms for blocking, and then maybe 10 different algorithms for matching, and you can actually use them. But we need to cover this whole process from data discovery, schema alignment, order of resolution, and actual matching and incremental processing of all the data that we need to process. So scenarios that we are addressing are complex. So I already mentioned search engines, and also many legacy and cloud migrations. There is much more in these problems than matching the two data sets. So all the schema alignments, data cleansing, standardization, preparation, order of resolution of data set, incremental processing, etc. So real life example, this is the project that we worked at with, and the client was one big global pharmaceutical company. So they decided to migrate to Salesforce, and they had like 64 offices in 64 different countries. And they had like maybe 15 or 20 different CRM systems. So they need to migrate all the data, consolidate, create golden records, because in many of those countries, they have same customers. And the problems that we are addressed, so different source schemas, different levels of data quality, sizes of data sets by several orders of magnitude. So, I mean, they will have like hundreds of thousands of or millions of customers in United States, but I don't know, in Montenegro or Slovenia, they may have maybe 500 or 1,000 customers. And different languages, so every company can use its own language, and not only the language, but also the alphabet. So maybe they have like Cyrillic and Arabic or whatever. My work is related to order of resolution. So what is the idea. So you have like 60 different datasets with different attributes. And how you will decide what will be the process and what dataset you will resolve first and what will come after that later in the process. This is like simplified scenario of the stuff that I have done. So basically, you have like 3 source datasets. You have defined target schema with 10 attributes. And those 3 datasets has different number of attributes and different size of those datasets. And if you can see, so dataset 1 and dataset 2 have overlapping attributes, as well as dataset 2 and dataset 3, but dataset 1 and dataset 3 doesn't have overlapping attributes. And if you try to match dataset 1 with dataset 3, you will not have any matches because you don't have anything to match by. So I defined several dataset attributes, and those are those 4. I will explain them a bit in more detail in next slide. So completeness. So that means compared to the total number of attributes, how many attributes I have in this dataset. Overlap. If I have 2 datasets, how many overlapping attributes do I have? If I have more overlapping attributes, there will be better candidate for matching because match will be more accurate. Inverse size. So this is related to performance. If I have the biggest dataset in process first, and then I match it with every other dataset, then I will need more processing power. So I would prefer to start with smaller datasets. And accuracy. So this is the measure of data quality of a dataset. So you can have a dataset that is quite sparse with attributes or not accurate with information. So you will have a tendency to start matching and working with more accurate dataset. So those are the formulas for completeness and those definitions that I have mentioned. Important thing is so completeness, inverse size, and accuracy are attributes of one dataset, and overlap factor is always defined for 2 datasets because you can see that dataset 1 and dataset 2 overlap in 4 attributes, but dataset 1 and dataset 3 overlap in 0 attributes. So if you have more attributes that are overlapping, then you will have the higher score for this. Yeah, so inverse factor. So basically, smaller the dataset, inverse factor size is higher. So these datasets should be processed earlier. And accuracy can be established by profiling, or we can get this information from somebody who's responsible for that source system and use it as a constant. And basically, based on that, I have created, experimented with the formula how to take care all of those 4 elements to calculate the final score and not the resolution. And I created pseudo algorithm that actually calculates all that scores, take the first 2 data sets, match them, remove them from the set of the data sets, and put back the combined data set, and then do the scoring again to find the third data set to match, and iteratively until all the data sets are matched. And this is also implemented not in R, but in Python, because it's easy to use. And what is actually work in progress, testing and experiments on open data. preparing for publication, so this is work that is still not published. And integration with other processes, so discovery, data cleansing, performance optimization, incremental resolution, that will result in more complex and complete framework that will actually be able to help business user to do the stuff they need to do. And a few conclusions. So it's widely used, very complex process. Academic and real-life challenges are very diverse. And a lot of work should be invested in building human-in-the-loop tools, scenario that will make real life problems easier and faster to solve. And that's great because I'm on time and I'm the only guy who's between you and lunch. And if you have some questions, I will be glad to answer.
There are no questions on the app, so do we have any question in the audience before lunch? Because we still have 5 minutes.
You may have questions. So the question is if something like this can be used to integrate medical data, and the answer is yes. That's exactly for what it can be used. Because when we talk about entity resolution, so usual example is people as entities. But it can be also used for products, books, venues, conferences, and also different types of locations, and also medical records. Everything that is string by nature, and so if you have a number, so 5 will always equal 5. So you cannot say, okay, 5 and 6 are similar, so we can find a similarity between 5 and 6. When something is numeric, it's always exact. But if something is string, then you need to use similarity algorithms. So basically, this whole process has a lot of different similarity measures that are like very, very wide area of data science. And I didn't cover this part at all in this presentation, but it's a huge field. So maybe just one more comment. So although a lot of data science lies on top of solutions that do this entity integration and entity resolution, this is basically more data engineering problem than data science problem. But the whole data science world is lying on top of data engineering. We have one more question.
It's clear how it can resolve syntax problems. What about semantic problems? For example, we have certain names that one data source can match with names in the other data source, but here it's a customer, while here it's a supplier. So how do we resolve that?
I mentioned this in this probability schema matching and alignment. So this is like one really big field that is covered by a topic that's called big data integration. And I can recommend you a really good book about that. It's written by Chin Luna Dong. It's called Big Data Integration. It's published by Stanley Morgan, and it's available for download. If you contact me, I will give you the link. So it's not easy, but basically it's based on that it's a very common example is airport. So basically, usually when you have flights, in those flights you will have flight origination airport and flight destination airport. But if you have just one airport, then you need to do the matching probabilistically with the assumption that it's like 60% probable that this is destination airport and 40% that this is source airport. And on top of that, then you have other problems because, especially on internet, you have some original sources of data and you have copies of the data. So to get the right matches, you need to recognize the copies and eliminate the copies from the matching procedure. So it's very, 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 very complex. A lot of reading.
No questions?
I have a question. Do you often, or how often is data lost during this process? And what are the measures to prevent that or manage that?
So that's interesting question, but it shouldn't get lost. But sometimes people doesn't do the controls for that. So in some cases, in some databases and even no SQL solutions, basically you don't, people sometimes don't think about controlling and testing and counting number of records at the start and number of records at the end. And this is very important. This is one of the human in the loop problems, because you have different systems, and basically you have some systems that will tell you, okay, this is bad record. Usually, I don't know, if you try to put character 100 in character 50 field, you can have several different results that are all valid and none is treated as default. So one result is substring and saving only first 50 characters. The second result is rejected record that is put in some rejected records table. And the third option is no answer. So record is rejected and dropped, but you don't have any information or it is not stored anywhere. But when you, as a data engineer or data scientist, when you develop such solutions, you need to know how your underlying technology and system is behaving to be able to do things properly. And that leads us to this topic where you have these two main reasons for failing. So you think you know what you're doing, but you don't, but you're doing the wrong stuff. And the other thing is that you don't know what you're doing. And if you come to the status and phase that you know what you're doing and you're doing this properly, then you are like a king of entity resolution and integration. Do you have?
Text that people
Mm-hmm.
what's the percentage of mistake and how you handle it? Or how you manage to do the correction?
So it depends. So you have sources when you have more errors, and you have sources when you have less errors. Sometimes errors are typographical errors, and then you can use different dictionaries with standardized names or last names, where you can assume and choose the closest name that corrects this. So you have a whole set of algorithms called n-grams, and the most popular is bigram, where you actually slice the string into pairs of two characters, first and second, second and third, third and fourth, fourth and fifth. And this type of algorithms is very useful for those kind of typographical errors. But first you need to profile data to see what are the patterns and what are the problems that you have, and then you apply these cleansing and standardization algorithms to prepare the data, and then do the blocking, and then do the matching, etc., etc. So each step in this process is very specific and require separate algorithms. So there is no such a thing as high quality and clean data. So it's always a problem. But the worst problems are when you have like IMBG numbers, which needs to satisfy some criteria, and if you put like 13 times 1, the criteria will be satisfied, and it doesn't mean anything. So those kind of stuff is something that you cannot resolve, because it's not error. It's just intentional overruling of the system controls.
Okay, thank you very much. If we don't have any more questions.
Thank you very much. If you have any other questions, I will be here today and tomorrow. And my colleagues, Tomislav and Dio, will have also tomorrow afternoon very interesting lecture about IPTV recommendation system.